So how about type 2 error? Well, this is the exact opposite. This is what is the probability of maintaining the null hypothesis, okay, accepting the null, not rejecting the null, as you sometimes have to say, where you actually should have rejected the null. Okay, so you tested a sample, you didn't see any enough evidence to reject the null, but really out there, fundamentally, there is a change that's happened. Okay, the sample doesn't fit the population. Okay, however, you just didn't pick that up in your sample, in your test. Okay, so the probability of that can be a little bit more complicated. Okay, and you do need some extra information. Okay, that thing I said at the end there, where actually there has been a change, there should have been a change that should have been spotted, that information needs to be given to you. Okay, so for example, with these European basketball players from type 1 example, what if the mean really is 203.9 for these players? The mean height, 203.9 centimeters. Okay, what's the probability of making a type 2 error? Okay, which is basically the probability of just not spotting that, not concluding that they are indeed shorter on average. Well, we can start off by finding the critical region. Okay, at what sort of mean sample height would we conclude that they are shorter? Let's see. Okay, we have normal distribution because our sample is big enough, bigger than 30. Okay, and measuring it from 205. Okay, what's this probability? Well, this probability is 5%. What is this upper bound, I should say? Okay, and that is the critical region, less than this upper bound. Okay, and to find an upper bound, that would be inverse norm. Okay, with 5%, 0.05, with a mean of 205, and crucially, well, you're going to have to type in the standard deviation. The variance would be, well, it was 26 for an individual, for individual players. We are going to divide the variance by 100 for a sample mean. Then we're going to do the square root of that to type in the standard deviation into our calculators. So it's inverse norm with 0.05, 205, and the square root of 26 over 100. Okay, so the standard deviation of sample means is greatly reduced from just if you were measuring one player, for example. Okay, and for that reason it gives you something that's actually quite close to 205, 204.161. Okay, so anything less than that, we would conclude that European players are shorter. Anything more than, we would conclude that they're not, and we would not reject the null hypothesis. Okay, type 2 error is what is the probability of not rejecting the null hypothesis, given that actually there is a shift, okay, given that in this case the mean is 203.9. Okay, so that is now the probability of getting greater than 204 given the mean really is 203.9. Okay, and you can visualize a new normal distribution of European players. Okay, and we're going to assume the same variance here. Okay, where we have 203.9 and we're trying to find this probability, okay, because this would be the probability given this mean of getting above our critical region, and therefore not ever rejecting the null like we should have. Okay, and that's going to use the same variance by the central limit theorem as we did before. Okay, but this is going to be normal CDF with a mean of 203.9 and with a lower bound of 204.161, upper bound of a high number. Okay, same variance as I said with the square root divided by 100, and we will see 30.4%. Okay, 0.304, and that is our probability of type 2 error for this normally distributed sample. Okay, so let's see this discrete, this Poisson example. What is the probability of a type 2 error here? Okay, a type 2 error would be if we scored less than 15, okay, or 14 or fewer goals, even though our attack has improved. Okay, so maybe it's later measured over the course of the whole season, or measured in some other way we're not sure of, and it's proven that their new mean is actually 2.4 per game. Okay, really this team is now scoring 2.4 goals per game. What is the probability of not spotting that? Okay, the critical region was 15 or more goals before, and therefore it would be the probability of scoring less than or equal to 14 goals with given a mean of 2.4. Okay, that's 2.4 goals in one game. Really, that doesn't make any sense to give it as one game, so let's convert that to 5 games, where it would be 2.4 times 5, that's 12. Okay, so really they should have been scoring 12 goals per game. What is the probability of just not spotting this improvement and therefore scoring 14 or fewer goals? And that's going to be Poisson CDF with 14 or fewer, so from 0 to 14 with a mean of 12. Let's go to our calculator, distributions. 1 second. And yeah, mean of 12, lower bound 0, upper bound 14 would give us 0.772. Okay, and that is our probability of type 2 error here, which is the probability of, given some new information about an actual improvement in our team's attack, what was the probability that in our 5-game sample we did not see enough evidence to spot that improvement, and we went with the previous null hypothesis anyway. Okay, and that is shown to be 0.772 in this case. Okay, and sometimes those type 2 errors can be quite high percentages, so don't be alarmed. The type 1 error is always going to be around the significance level or slightly less than the significance level. Type 2 error is really highly dependent on this new information that you're given. Okay, sometimes it might not be clear which kind of calculation you need to do. If you're given that new bit of information, you can expect a type 2 kind of question, that's for sure. Okay, and it will essentially, it will have to tell you what is the probability of type 2 error, so it shouldn't be too cryptic,